Good morning, everyone. My name is Praful Badgaya. I am a final year student at NIT Raipur. Today, I am recording the demo video for the faculty role selection at Akash Bajus. I have the teaching experience of 1 year as a tutor. Also, I am a subject matter expert at Czech India Limited. For today's demo video, I have selected the topic of chemical kinetics. So, let's begin with the topic. Chemical kinetics is a branch of physical chemistry which deals with the study of the speed and the rate of the chemical reaction and the factors which affect the rate of the reaction. The factors are like the temperature and the catalyst. When we just increase the temperature, then the rate of reaction goes on increases, and the catalyst help us into just increase the rate of reaction without affecting the or without taking the part in the chemical reaction. And we also see about the mechanism of the reaction, how it depends on a particular reaction in the chemical kinetics. Then rate of the reaction, it is a change in concentration of the reactant or the product with respect to time. Here the reactant R get converted into product P, and with the passage of time the concentration of reactant get decreases and that of product get increases. Then the rate of reaction is equals to decrease in the concentration of the reactant divided by change in time, and that is equals to increase in concentration of product divided by change in time. Then the rate of the reaction in terms of reactant and product can be written as rate of reaction is equals to minus del change in concentration divided by del T, and that is equals to plus del change in concentration of P divided by del T, where del change in concentration of R, it means here the concentration of reactant R goes from R1 to R2, and del P shows that the change in concentration of product from P1 to P2. Del T shows that change in time from T1 to T2. Here we just need to understand that why we take the sign negative and the positive. Here negative sign shows that there is a decrease in the concentration of the reactant with the passage of time, and there is an increase in concentration of the product as soon as the time passes. Then we are going to look at the instantaneous and the average rate of the reaction. First we look at the average rate of the reaction. At the left hand side we have the graph that change the concentration of the reactant get decreases with the passage of time. At t is equal to 0 we have the total concentration R naught, and as soon as time goes on increases the concentration of the reactant goes on decreases. At starting we have the T1 time, here the concentration is C1, and time T2 we have the concentration C2. Then the R average is denoted by minus del change in concentration of R divided by del T, that is equals to minus C2 minus C1 divided by T2 minus T1. And when the time difference between the T1 T2 get very small, it means that as soon as it tends to 0, then it becomes the instantaneous rate of reaction. And instantaneous rate of reaction is a kind of derivative of the concentration with respect to time, that is equals to slope. We have seen in straight line that we have the equation y is equal to mx plus c. When we just differentiate the y with respect to x, we get the dy by dx is equals to m. Here m is the slope, and this particular line which touch the graph of this change in concentration at one point, which shows that this has the slope negative, because when we draw angle theta, that angle is greater than 90, which shows that here slope is the negative. And in the right hand side we have the graph for the change in concentration of the reactant with the time. Here the at T1 we have the concentration C1, at T2 we have the concentration C2. As soon as time goes on increases, the concentration of products goes on increases. It means rate will be increases. And then here the R average is equals to del P divided by del T. It means C2 minus C1 divided by T2 minus T1. As the change in time goes on decreases, it becomes instantaneous rate of reaction, that will become d by dt of change in concentration of product, and that is equal to slope. Here the slope touch at the single line, and as soon as we just draw the theta here, we see that this angle is less than 90 degree. It means here slope is the positive, and we see that the rate of a reaction at particular time interval is known as the average rate. And when we just more specific about any particular time, then it becomes instantaneous reaction. Then why we are using del and d signs, we should know that del sign shows that there is a change in concentration with respect to a larger interval of the time. And when we see the change in concentration at any particular specific time or instant, then we use d. Rate of reaction in terms of disappearance and the formation. Rate in the change in the concentration of reactant or product with respect to time. Here we have the product A which get converted into B. Then there is a change in concentration of A and B. Then the rate is equals to minus del change in concentration of A divided by del T. And here the for the product side, rate is equals to del change in concentration of B divided by del T. When we do not include the stoichiometric coefficient of any general reaction, then it becomes the rate of disappearance for the reactant side, and the rate will become the rate of formation when we do not include the stoichiometric coefficients of any general reaction. Then we are looking at the expression of the rate of the reaction in terms of different reactant and the product. Here we have the reactant capital A and capital B, and here we have the product is capital C plus capital D, and the small a, b, c, d are the stoichiometric coefficient of this reaction. So the rate for this reaction will be the change in concentration of A divided by time, and it will be divided by the stoichiometric coefficient of A. Here here it will be minus 1 upon B change in concentration of B divided by del T, and that will be equals to 1 upon C change in concentration of C divided by del T, that is equals to 1 upon D change in concentration of D divided by del T. Here capital A, B, C, D which are in the square bracket shows that these are the concentration of the A, B and C respectively, and this reaction is valid for the homogeneous system. If the del A is equal to change in concentration, it means if we have the single phase, it means suppose we have the A, B, C, D all in the gaseous phase, then we need to find the rate in terms of mole per liter per second. But when we have the heterogeneous system, then we need to find the rate of a reaction in terms of mole per second. Heterogeneous system means that when we have the more than one phase. Rate of a reaction and the rate constant. According to the law of mass action, rate of any reaction is just directly proportional, and that is the product of the concentration of the reacting species and which has the power, and that particular power we need to determine by the experiment. And we have the given one general equation here, capital A, B, C and D shows that the reactant AB and C and D shows that they are the product, and small a, b, c, d are the stoichiometric coefficient of the reactant and the product respectively. Then the rate of the reaction on the basis of the mass action become rate is directly proportional to concentration of A to the power x, and multiplied by concentration of B to the power y. Here exponent x and y may or may not be equal to the stoichiometric coefficient which was A and B in the last rate law equation, as we have seen. And we have seen that whenever we just try to remove the directly proportional constant, we just need to add some constant so that the equation can be balanced. Then the rate is equals to k a to the power x and b to the power y. Here k is the rate constant, and the rate constant depends on the catalyst and the temperature. Then the change in the concentration of R divided by dt is equals to k a to the power x and b to the power y. Rate law is an expression in which rate is given in terms of molar concentration of the reactant, with each term raised to the power which may or may not be the same as the stoichiometric coefficient of the reacting species in the balance equation. Whenever we have the any general equation, we just cannot tell by just looking at the stoichiometric coefficient. We just need to do some experiment, and that particular experiment tells us about that the what will be the power of that particular rate of reaction. And then the next topic is the order of the reaction. Order is the sum of the power of the concentration of the reactant in the rate law expression. it means that in the last rate equation we have the power x and y of the reactant A and B. Then the sum of these powers will be x plus y, and this is the order of the reaction. Here x is the order of the reaction with respect to A. It means x was the power of A, and the y is the order of the reaction with respect to B. It means the y was the power of the B. Order of a reaction is the experimental quantity. It is calculated by experiment, not directly. We are unable to tell just directly looking at the reaction. Order of a reaction may be positive, negative, or zero, or it may be fractional. Then the molecularity of the reaction, the number of the reacting species taking part in an elementary reaction, which must be collide simultaneously in order to bring about a chemical reaction, and that is called the molecularity. Whenever we have the any reaction, then we just need to see that how many molecules at any particular time can effectively collide, so that that particular reaction will proceed in further direction, so that the product will be formed. So we should need to look at that how effectively these molecules are able to collide, so that there has to be any effective collision from that, so that the good amount of product has to be formed. And molecularity is always a positive whole number, like it will be 1 2 3. Like molecularity is the sum of stoichiometric coefficient of the reaction, and molecularity never be greater than 3, or maximum it goes to 3. We have the example of molecularity. Here PCl5 get converted into PCl3 plus Cl2. Here we have the one molecule of PCl5. So this one is the unimolecular reaction, and in the second reaction we have the 2Hi which get converted into H2 plus I2. Here two molecules of Hi get simultaneously collide. So this reaction is the bimolecular reaction. And in the third example we have 2SO2 plus O2 that convert into 2SO3. Here two molecules of SO2 collide with the one molecules of the O2, and here we have the effective collision of three molecules. So this reaction is the trimolecular reaction. The reaction having an individual order on the or the overall order zero, fractional, negative, then that particular reaction must be a complex reaction. Complex reaction is like that which take place in more than one steps. And for the complex reaction, the rate of the reaction is determined by the slowest step of that particular reaction. Then slowest step is called the rate determining step. Thank you from my side.